All right, everybody settle down. Welcome to the hybrid colloquium. It's my distinct pleasure today to welcome Cora Dvorkin, professor in Harvard physics. Cora grew up in Argentina and got her bachelor's degree from the University of Buenos Aires. And then she went to do a PhD at Chicago with Wayne Hu and a postdoc at the Institute for Advanced Study, and then here at the ITC. Then she went over to the other side of campus to physics as faculty. So she's interested in early universe physics, dark matter, neutrinos, inflation. She's involved in CMB, strong lensing, and galaxy surveys. She's on the board of I5. She's an S4 at LSST. She's the winner of the 2018 Harvard Foundation Scientist of the Year Award and a Redcliffe Fellowship. And she also has a DOE Early Career Award. So today, Cora is going to tell us about unlocking new physics.
Thank you very much. Hello, hello. Is my mic on? Yes. Excellent. So thank you very much for the invitation and the kind introduction. And I hope everyone is doing well in these still difficult times that we are living. So I'm very happy to be here, and the fact that this is my first in-person talk in more than 2 years. So this is quite exciting. So today I will be telling you some of our efforts with my research group to unveil new physics out of astrophysical data sets, both from small and large scales. So here's where we stand in cosmology today. We have a standard model of cosmology known as lambda CDM. And this model has been extremely successful on cosmological scales among a wide variety of different observables, from the cosmic background temperature and polarization fluctuations to the clustering of matter to the expansion history of the universe. I'm showing you here in this plot, you can see the matter power spectrum as a function of wave number. In black, I'm showing here our prediction from our lambda CDM standard model of cosmology. And the different points over here correspond to different measurements interpreted within the context of this model. So what's interesting about this figure is that it's spanning 14 billion years of history of the universe. It's spanning 4 orders of magnitude in each of the axes, and we can see how a wide variety of cosmological observables are fit by the lambda CDM model quite beautifully. However, we still have fundamental questions that are still unanswered. What is the physics that sees the first structures in the universe? What is the source of the accelerated expansion of the universe? And what is the nature of dark matter? And it's in this last question that I will focus my talk today. So what do we know about dark matter? Well, we know that it doesn't emit or absorb light in any significant way, so we might as well call it transparent matter. But it does have mass, so it exerts gravity on visible particles. This is how we literally know everything else about dark matter. We have learned from cosmological observations that dark matter constitutes about 84% of all the matter in the universe. It's all around us, and we know it forms the scaffolding for the visible universe. But there are no really good candidates in the standard model for dark matter. So we still have open questions. What it is made of? Does it interact with ordinary particles? If so, what are these interactions? And let me illustrate here our relative ignorance by focusing on just one parameter, the mass. It turns out that the mass can range over about 90 orders of magnitude, going from very light dark matter, for example, axions, to the famous WIMP, to compact objects. So this is a huge range. A related question that I will be asking, and that one could ask, is could there be new light particles produced in the early universe beyond the standard model of particle physics? And if so, how can we measure them? So the plan for this talk will be to walk you through our efforts for unlocking new physics out of astrophysical data sets, both at large and small scales, but I will start from the smaller scales. So as I just mentioned, in the past few decades, we have measured the large-scale structure of the universe very accurately, and this has allowed us to put precision-level limits of different types of dark matter scenarios. However, on smaller scales, there is a lot of data, there is a lot of structure, and it is not as well understood. Furthermore, many dark matter scenarios that agree mainly by construction at large scales show differences at small scales. So observations at small scales provide fertile grounds for testing different dark matter scenarios. As an example of the effect of that dark matter models can have on subgalactic scales, I'm showing here two different projected dark matter densities coming from high-resolution embodied simulations. One coming from a simulation of cold dark matter in the CDM paradigm, and the other one coming from a simulation that has some exotic dark matter microphysics that results in dark matter clumps that are more susceptible to tidal stripping. So you can already see by eye that there is a lot more structure here in the CDM paradigm compared to here in this exotic dark matter scenario. And this is just to illustrate the fact that dark matter physics can lead to interesting phenomenology that is observably different from CDM on these scales. So the idea will be to probe dark matter distributions on small scales, and by this I mean kiloparsec scales, to falsify or corroborate the CDM paradigm. And our tool for this will be strong gravitational lensing. So let me give you a review in one slide of gravitational lensing. So we will have a background source, which in our case will be a galaxy. And we will have a foreground galaxy between us, the observer, and the background source that deflects the light that is coming toward us because of its gravitational field. So from our perspective, we can see arcs over here. And the idea will be to use these images to see if the lensing galaxy is clumpy or smooth. Okay, so that's the main idea. And this idea that has been suggested about 20 years ago by Mao and Schneider, tells us that, so the idea is that substructure that lives in the halos of the lensing galaxy can locally perturb lensing images. So by looking at the residual between the smooth mass and what is actually observed, we can infer the presence of substructure. Okay, so the advantage relative to other methods for detecting dark matter is that we do not need to assume a specific coupling between dark matter and the standard model sector. So in this sense, I like to say that we are model independent as opposed to, for example, what happens in direct detection searches or indirect detection searches. Furthermore, the lowest mass subhalos are largely devoid of stars. So detecting them with the gravitational technique is the only possibility since these subhalos cannot be seen directly. And so with my group, we have done work in this arena following two different but complementary approaches. The first approach is what I call direct detection approach, where our goal is to resolve individual more massive perturbers and from there infer their properties. The second approach is what I'm calling here indirect or statistical detection approach, where we want to marginalize over individual subhalo properties to learn about subhalo population characteristics. And so here we will be exploiting the steepness of the subhalo mass function, the expectation that we have many low mass subhalos to try to statistically detect their collective perturbation on images. And so I will start with the direct detection approach, which is the most intuitive one. And once we understood this approach, we will move on to the statistical one. So we will have the same picture as before, but now we will add one subhalo in the halo of the main lens or more than one. And we will look for small deflections of the light as it comes from the source and it crosses the lens. And so one of the main methods used for direct detection of subhalos is known as gravitational imaging. Much like what Mao and Schneider proposed, the underlying principle here is that if you have some dark matter clamp lying close to an imaging projection, there might be some visible distortion that you can try to reconstruct. Okay, so this figure that I took from a paper by Simona Beghetti and collaborators about 10 years ago very nicely illustrates the pipeline that goes behind this. Basically, you start from the data, a strong lens image in our case, and you have to model the smooth component of the object doing the lensing, assuming that there are no dark matter clamps in it, and you have to model the source. Once, somebody's talking? Okay, anyway, once we have these two ingredients, you can try to reconstruct, you can minimize the smooth image and the data to minimize the residual of them. And so in minimizing the residual, you can try to reconstruct the surface mass density or the convergence field. And so you can see that in this figure, Beghetti and collaborators found an overdensity over here, and this was a 10 to 12 sigma detection, claimed detection of a subhalo in this position in the image. So far, using this method, there have been about 3 subhalos detected in the order of 10 to the 9 solar masses from about 30 images analyzed. What I want to emphasize here is that this is a very computationally expensive process that can take months to analyze a single system. So if you have tens of images that you want to analyze, that's okay. But in the next few years, we expect tens of thousands of these images to become available from this type of science through the Vera Rubin Observatory and other experiments, in addition to further follow-ups, of course, by the HST, ELT, etc. And in fact, there are already many recently discovered by the Dark Energy Survey that are waiting for follow-ups. So this is great, since this vast increase in sample sizes will provide a leap in our understanding of dark matter. But obviously, it is unsustainable to take months to analyze each image. So what motivated us, together with my former PhD student, Ana Diaz-Rivero, was the following question. Can we automate a procedure like direct detection using machine learning, making this process much faster? And if we understood the sensitivity of our machine learning model well enough, we could still combine detections and non-detections to probe different dark matter scenarios. So we turned the problem into a binary classification task, and we asked the question, for what subhalo masses is the network able to recognize the lens as having a subhalo versus not having any? And since most of the images analyzed generally yield non-detections, this could cut down the analysis time by a large factor. And so in this work, using a very simple architecture, we use the convolutional neural network here, we found for realistic levels of Hubble Space Telescope noise that we could be sensitive to subhalos of masses around 10 to the 9, a few times 10 to the 9 solar masses, which are numbers that are comparable to the numbers cited in the literature for real detections, even in the presence of correlated noise, which we also tested for. So we found these results very promising, since they show that we could accelerate the process of discovery by many orders of magnitude, basically from months to much less than a second, of course, once the machine learning, once the network is trained. And this was done for the first time in the literature for direct detection of substructure as a proof of principle. But of course, we knew that we could get even better results by further optimizing and changing our architecture. And so this is what we did next. We took the problem a step further and tried to cut the middleman entirely. We tried to convert the entire detection pipeline into an image segmentation task. Image segmentation is basically the process of taking an image and analyzing what each of the components of the image are. To do this, with my former postdoc, Brian Osdek, we used a network called UNet, a network architecture called UNet. UNets are networks that are well known for their success on image segmentation in biomedical research, and since then they have been used more and more in astrophysics. So here we taught the network to reconstruct the convergence field by classifying every single pixel in the image as belonging to the background, the main lens, or one of various different subhalo classes. And so the input is a strong lens image, and the output is the probability for each class. So here I'm showing you confusion matrices for 2 different types of noise, different orbits of HST. And you can see here how the network struggles to find the lower mass subhalos. And this is because the level of noise here is just above the pixel brightness variations due to the presence of these subhalos. And in the paper, we provided an exact mapping that helps us understand exactly why we lose sensitivity in the places that we lose sensitivity. But we also saw that it does fairly well for subhalos around 10 to the 9 solar masses, which again are numbers that are comparable to the ones cited in the literature using standard methods. Moreover, we showed that the network can actually find not just one subhalo at a time as it was trained for, but many at a time, as I'm showing in this picture over here. So we can combine many of these images to put constraints on the logarithmic slope of the subhalo mass function. And well, we do this in order to gain insights on the nature of dark matter. So we can see here how, of course, by combining many images, our error bars get reduced. And for example, if you see when we combine 1,000 images, we can get down to 10% error bars. So this is quite exciting. In fact, I think we have exciting years ahead of us in the large number of opportunities machine learning is bringing and will continue to bring to the field. And Harvard has been quite involved in this with the IFI Institute and NSF AI Center that we started with MIT, Tufts, and Northeastern, and some colleagues over here, the Harvard Data Science Initiative, the Institute for Applied Computational Science, I think this is what it stands for. And we have also written white papers for the Astro Decadal survey 2 years ago, and we are submitting a white paper for the snow mass process this year. So these are quite exciting times. Okay, so let me switch gears now and talk about the statistical approach, where we marginalize over the individual subhalo properties to learn about the population characteristics. So the actual statistical observable that I will be talking about is the convergence power spectrum, where again, the convergence is just the surface mass density. And the convergence power spectrum is quite attractive for the task that we have to deal with because it provides a nice bridge between what we observe, strong lens images, and what we want to gain some insight into dark matter theories. And it does this by relating lens scales, which are basically deflection vectors on the lens plane, to mass scales, which is what dark matter theories are actually predicting. So the convergence power spectrum is a neat bridge between the 2 sides of this diagram. So I will start here by considering the limit in which all the perturbers are substructures that live in the lens plane. And once we build intuition and understand how different dark matter microphysics affect this observable, we will move on to the much more general and complex case of a distribution of 3D perturbers. So in a paper, again, with Anna and Francis Yancy Racine, a postdoc at, a former postdoc at Harvard, who is now a professor at the University of New Mexico, we developed a general formalism to study the endpoint function of the convergence field. And we started from the power spectrum. So if we have, the idea is that if we have a lot of substructure, the central limit theorem will kick in, the perturbations will look very close to Gaussian, and all the information will be contained in the power spectrum. That's the limiting case. So what we did is we modeled the convergence field as a fluctuation field superimposed on a smoothly varying background profile of the coast. Sorry, this is the substructure convergence field, and this is the smoothly varying background. And we can see that the substructure convergence field depends on the position of subhalos, the mass, and intrinsic properties of the subhalos that may determine the density profile of the subhalos. So here we propose a change of language. Instead of talking about subhalos, we propose to talk about correlation functions of the projected density field. And so the advantage of this is that we don't need to define what we mean or don't mean by a subhalo, as is generally done in the literature, and sometimes with different definitions. So we started from first principles. This has been done in the large-scale structure community a long time ago. And since I was more familiar with this when I started working on this field, I adopted the same kind of philosophy. So we describe the power spectrum in terms of what we call a one subhalo term, in analogy to the one halo term, which arises from ensemble averaging over the spatial distribution of single subhalos. And we also define a two subhalo term, again, in analogy to the two halo term, which comes from averaging over different pairs of subhalos. And note that here we are taking integrals of the probability distribution of the mass, the intrinsic properties, and the distribution of the subhalos within the host. So here's our power spectrum. I will be showing you in the plots that will come from now on, I will be showing you the one subhalo term. If you're interested in the two subhalo term, let me know at the end of the talk, but it will basically fit in at these very large scales. So what we saw is that the power spectrum is mainly described by three quantities. At low K, we have a constant amplitude, a plateau. We are looking at scales that are much larger than any subhalo in the system. So basically they appear as point masses, and the Fourier transform of that is white noise. So we see this plateau. As we move on to smaller scales, we see a turnover scale, and this turnover scale is given by tidal interactions of the largest subhalos in the system. And as we keep moving to the right to even smaller scales, we reach an asymptotic regime where the power spectrum asymptotes to a power law. And this law reflects the properties of the inner density profile. The slope over here reflects the properties of the inner density profile. So in particular, for an NFW profile, which is used to describe the CDM scenario, this slope goes as 1/k to the 4. Now, if we have a non-trivial dark matter scenario, and as an example, I chose a self-interacting dark matter scenario, the inner density profile will change. For this scenario in green over here, the inner density profile has a core. Okay, so this will change the power spectrum slope, and in this case, it will go as 1/k to the 8, okay, reflecting the fact that the inner density profile looks different in this case. So here we have a promising theoretical prediction to distinguish different types of dark matter scenarios. However, notice that these are very small scales that I'm talking about. I'm talking about scales that have wave numbers of 50 inverse kiloparsecs or smaller than that. And so these scales will be hard to reach by near future experiments. However, as we saw later, by adding redshift information, we can gain information from larger scales that now, yes, will be accessible by near future experiments. And this is what I will show you next. Let me now discuss the redshift evolution of this observable. These are results coming from high resolution embodied simulations that our colleague at MIT, Mark Vogelsberger, has provided to us. On the left over here, I'm showing you the evolution in time in a CDM scenario. So as we go up, we evolve in time, okay? And as you can see, the evolution here is quite intuitive. The amplitude is increasing, and this is because we are accreting more and more substructure as time goes on. Here on the right, I'm showing you an exotic dark matter scenario that is given by a low mass cutoff in the initial power spectrum and dark matter self-interactions, okay? This is within the context of ethos simulations, if you're familiar with them. And so this scenario results in dark matter clumps that are more susceptible to being tidally disrupted. And you can see this is reflected in the fact that the amplitude got stalled here from redshift 0.5 to about 0. And this is because the accretion in substructure is being compensated by substructure being destroyed. So there is a net transfer of power from large scales to smaller scales. And this, you can see this in the change in the power spectrum slope between redshift of 0.5 and 0 at wave numbers greater than about 2 inverse kiloparsecs. And now note that these are scales that will be accessible by near future experiments. So here you can see in a plot that I took from one of Francis Yan's papers, the scales that we will be able to probe with using a near future space-based and interferometric observations. And you can see that we will be able to reach tens of inverse kiloparsecs in the near future. So I just told you how the convergence power spectrum of subhalos within lensing galaxies is a promising observable to study dark matter and to try to discern between different dark matter scenarios. However, the distances involved in strong lensing are vast, and we expect the relevant volume to contain line-of-sight halos that are not necessarily associated with the main lens. And so in research, I want to tell you about recent work that we did with my group. In particular, I want to emphasize work by two of my PhD students, Chan Sengul and Arthur Sang. In collaboration with collaborators at Berkeley, we developed a formalism to calculate the effect of line-of-sight halos as an effective convergence power spectrum. And so now, instead of having a single lens plane, we will have a sequence of lens planes corresponding to these perturbers. And instead of having a vanilla lens equation, we will have a recursive lens equations that couples different deflections at different positions. So by assuming that the perturbations of the line-of-sight halos are small, we show that they can be projected onto the main lens and treated as effective subhalos with an appropriate weight. And we tested our formalism against numerical simulations, and we found excellent agreement. So we wanted to study the relative contribution of line-of-sight halos and subhalos for different parameters of the system. So here we studied the relative contribution in terms of the source redshift and the lens redshift. Here, for this example, I'm fixing the amplitude, I'm fixing the halo mass function, and I'm varying the amplitude of the subhalo mass function in this parameter F sub over here, which is the fraction of dark matter halo mass in substructure. So redder colors show that line-of-sight halos dominate, and bluer colors show that subhalos dominate. Pre-intuitively, if you move from here to here, you see that bluer colors start dominating. But which of these panels are we observing in practice, right? That's the question. We don't know exactly what the value of F sub is, but we see from different values that taken from the literature, from upper limits in the literature, that a scenario like this one for the mass scales we are considering in this problem is very unlikely. A scenario like this too is much more likely, but we are sitting in a scenario like this one, in which you can see that line-of-sight halos are dominating. And why is this important? Well, here I overlaid a series of points coming from the Bells and Slats families of galaxy-galaxy lensing. These are two well-known high-quality sets of lensing systems. In particular, these are sets that have been used to place constraints on dark matter. And we can see that for both sets, for a fraction of substructure that we think is more realistic, these systems are likely dominated by line-of-sight halos as opposed to subhalos, as they were assumed to be in previous studies. So what I want to emphasize here is that in order to translate a measured power spectrum to a dark matter theory, it is important to understand whether the subhalos in the lensing galaxy or the line-of-sight halos are the dominant contribution to the power spectrum. Otherwise, we can obtain wrong inferences about the nature of dark matter. And the fact that for typical lensing configurations, the line-of-sight halo contribution is dominating should be good news. At least for us, it was good news in the sense that the subhalo mass function is very hard to pin down, but while in comparison, line-of-sight halos live relatively calmer lives. And in terms of current data, we are reanalyzing systems that have been claimed as subhalos in the literature, and our analysis indicates that it is likely that many of them are halos along the line of sight. In particular, this system over here was claimed to be a subhalo in a Nature paper that I showed you about 10 years ago. And these are our results from our Markov chain Monte Carlo likelihood analysis, where we vary the parameters of the source and the lens. And we find that the system is indeed more likely to be a line of sight halo. Our analysis also indicates that this structure is more massive than previously claimed in the literature by about an order of magnitude. Okay, so in the time that remains, I'm exactly at 4:30. So in the time that remains, I will now move on to talk about how we can use the larger cosmological scales to learn about the dark sector. So we can attempt to learn about the dark sector of the universe at a wide range of scales using different cosmological observations. And these are just some examples of work that I have been doing with my group to try to understand the nature of dark matter at different scales. Dark matter analysis in cosmology have the huge advantage of not having to rely on assumptions about the dark matter density in the neighborhood of Earth, as opposed to, for example, direct detection searches. For example, I'm going to show you some examples, and then we will zoom in the example that I will be talking about until until the talk ends. So this is one example in which we showed how we can use 21 centimeter observations at cosmic dawn to learn about dark matter fluctuations at scales of about between 10 and 80 inverse megaparsecs. In red and cyan, I'm showing you here the error bars coming from different types of 21 centimeter observations. And you can see here in this example how we can use these measurements to discern between different dark matter scenarios. So for this, we use 21 centimeter observation. In another example, over here, we have been using CMB data and tracers of the matter fluctuations. This is an example of the power of larger scales, where we tested a general dark matter scenario known as freezing. The freezing mechanism for dark matter production is a compelling alternative to the famous freeze-out mechanism, where here instead dark matter is being produced by feeble interactions of standard model particles. In this series of works with my collaborators, we identified a new channel for dark matter production coming from the decay of photons that acquire an in medium mass, okay? We call them plasmons. So these plasmons decay turn out to be the dominant channel for dark matter production at sub-MeV scales. And we show that using existing data from the CMB, from the Planck satellite, we can rule out masses of dark matter that are below 19 keV. And we also show that using future CMB data coming from, for example, CMB stage 4 and other probes of structure formation, we can do even better. So this scenario necessarily implies that there should be some dark matter baryon interaction. And in fact, this became one of the main science drivers for the dark matter science case in the CMB stage 4 collaboration, which is a next generation CMB experiment that I'm part of together with other people here at the CFA. Moreover, this is exciting because it's completely complementary to planned direct detection searches, which will test. Some of these searches have been claimed to be able to test down to 10 keV. So this is very complementary, and that's why we find this exciting. Okay, so I will focus now and for the rest of the talk on a program that I'm very excited about. In a series of work with my group, in particular with two of my PhD students, Nick DePorcio and Linda Su, who is now a postdoctoral fellow at Berkeley, and Julian Munoz, who was my former postdoc, and you'll know him because he's here as a Clay Fellow. We proposed a new way to look for particles beyond the standard model, to look for light relics, using CMB observations and galaxy data. So I will tell you about this. The question that we asked is, could there be new particles that decouple at some point in the whole thermal history of the universe between inflation and an MEV? And if these particles are light relics, which means that they decouple while relativistic, they should survive until today, just like neutrinos do. In fact, neutrinos are considered light relics. And if so, they should have an effect in the large-scale structure of the universe, so we can use cosmological observations to go after them. And since these particles are beyond the standard model, they should also be, they could also be part of the dark sector. So, well, as I said, a well-known example of these light relics are cosmic neutrinos. Neutrinos were in thermal contact with the rest of the plasma in the very early universe, and at some point they decouple. And we can understand the temperature of decoupling by basically doing some dimensional analysis. And if you do the exercise, you will find out that they decouple at about the temperature of an MEV. And this was right before electron-positron annihilation. And so when this happened, when electron-positron annihilation happened, they deposited the entropy into the photons. And so because the neutrinos were no longer in thermal equilibrium with the photon baryon plasma, this heated up the photons. And this is why now we observe a different temperature for the cosmic microwave background and for the cosmic neutrino background. It is, let me mention here that it is conventional to define this factor N effective, that is a measurement of the energy density of relativistic neutrinos, and in the standard model, it should be 3.045. So to give you an idea of what the numbers are for the different quantities involved, I'm showing you here a plot of the temperature of the relic today versus the temperature of decoupling, okay? So you can see that particles with an earlier decoupling temperature are colder today. And this is because they stopped talking to the rest of the plasma earlier on, while the rest of the plasma kept getting heated up because of degrees of freedom that disappear. So you can see this in this purple line over here. Again, neutrinos decoupled before electron-positron annihilation, and their temperature today is 1.95 Kelvin over here. For decoupling temperatures high enough for which we have counted for all of the degrees of freedom in the standard model, we are being conservative here, we are just considering the degrees of freedom of the standard model, then the temperature today should be 0.91 Kelvin. So if there is a relic at some point, we should expect that the temperature today is between 0.91 Kelvin and 2.7 Kelvin. And this is the most conservative scenario in which we have a minimal extension relic. Okay, so as a result, you can go look for any particle that decouple at some point and parameterize it by its temperature today and its degrees of freedom. And so if the relic is relativistic at all times, we can capture the contribution to the radiation energy density through this factor N effective. So the idea will be to look at this N effective number, and as I mentioned, for the standard model, it should be about 3. So any number that is not 3 is telling us that there should be something else other than neutrinos in the light relic component of the universe. So the contribution of a relic will be proportional to the temperature today to the 4 times the number of degrees of freedom. And this purple line over here that I showed you before corresponds to scalars, okay? So as you make the temperature lower and lower, the contribution to N effective gets lower and lower. So you can see that the contribution can go from basically order unity to about 0.027. And in fact, this number 0.027 is one of the targets of the next generation CMB stage 4 experiment. So what's the effect of N effective on the CMB? Well, as you change N effective, you change the expansion rate of the universe, which in turn affects the CMB damping tail. Okay, so the Hubble rate contains basically controls the amount of diffusion of photons diffusing out of the gravitational wells. This is called field damping. And so with more N effective, the sound waves get more diffuse, and therefore by measuring the damping of the CMB, you can get tight constraints on N effective. So the best limits come from Planck, currently come from Planck, and are of delta N effective of about 0.2 at the 95% confidence level. So we can rule out anything, any particle that decoupled after the QCD phase transition. But there could still be particles that decouple before the QCD phase transition. And the hope is that CMB stage 4 will be able to bring down this number to about 0.2 to 0.3. And this is great. But in the best case scenario, we will be able to see a hint of it. If there is a new light relic particle, CMB stage 4 should be measuring this number at about the 2 sigma level. So if there is a new particle, we should be able to see a hint of it. Something interesting that you can ask is, what happens if these relics aren't massless? So we gave these particles the acronym LIMERs, light but massive relics. They are relativistic at decoupling, that's why they are light. They behave as matter today, and they are relics because they were in thermal contact with the standard model, just like neutrinos were. So I will tell you about now a dedicated search that we did for these particles. The idea will be to, instead of looking at a 1D plot of just the temperature and effective, we will be expanding this plot to look for the mass of these particles. So what do lemurs do to the large scale structure of the universe? This is a cartoon to point out that the gravitational evolution is different for particles that are fast moving versus particles that are slow moving. Just like in the case of neutrinos, small scale density perturbations grow more slowly than large scale density perturbations, and the relevant physical scale of the problem is the distance a lemur can travel in a Hubble time. So we will have a suppression in the matter power spectrum at scales that are smaller than the lemur's free streaming scale. And the lemur's free streaming scale is given by the ratio of the mass and the temperature. And the size of this suppression is given by the current abundance of the present abundance of lemurs, which is given by the mass times temperature cubed. So now you can hope to measure both parameters using large scale structure observations, not just a degenerate combination of the two. And this is the idea. Now we went ahead and did a scan for lemurs using CMB data from Planck, galaxy data from BOSS, and weak lensing data from CHF-T-lens, marginalizing over lambda CDM parameters and neutrino masses and bias parameters under the effective field theory paradigm. So we didn't find them in the data, to make the long story short, but our work set the best constraints on lemurs that we have up to date. Anything in the color band is currently allowed, okay? So we can see that for very low masses, we recover the delta and effective bound found by Planck, so this is good. But you can make the lemur heavier and heavier, and you can see how we start deviating from this bound. And you start getting more stringent constraints. So this is an improvement over an effective. All this region is now allowed. And so we classify the lemurs by their spin. You can have a scalar like an axion, a vector like a dark photon, a Weyl fermion like a gravitino or a sterile neutrino, and you can also have a Dirac fermion. And these are limits that we found at the minimum temperature of 0.91 Kelvin. So we are being super conservative here. And so using all this complementary data helped us to set the best limits on relics. And an interesting case is that of the gravitino. Using our limits, we can say that the gravitino mass has to be below 2.3 electron volt, which is about a factor of 2 better than what we had with the CMB, and about almost an order of magnitude better than what we had with the Lyman alpha about 15 years ago. This is interesting because it can be translated to an upper limit on the SUSY breaking scale for this type of models, which now, taking this number into account, can be translated into a limit of less than 70 TeV, which is in strong complementarity with lower bounds coming from colliders. Okay, so I will end my talk here with a few concluding thoughts. I divided my talk in terms of scales. For the smallest scales, we focus on a purely gravitational technique, strong gravitational lensing. And I showed you how we can use gravitational lensing to probe dark matter fluctuations at about kiloparsec scales, which is a regime that so far has remained much less tested than the large-scale structure of the universe. I told you about ways of enhancing direct detection using machine learning. And I also talked about the statistical probe, the power spectrum, the convergence power spectrum, which has the advantage that is sensitive to lowest mass subhalos, and it provides a more direct link to dark matter theories. Finally, I showed you how we think that line of sight halos are likely the dominant contribution for typical galaxy-galaxy lenses, and that I think this should be good news for the ability to draw conclusions about the nature of dark matter in an unbiased fashion. For larger scales, we focus, I told you about many things, but we focus on the search for light but massive relics, lemurs. The search for lemurs, we think it complements efforts on N-effective, opening a new route for finding physics beyond the standard model. We set the best limits up to date with current data, in particular with the help of large-scale structure data. And finally, looking at the future, we think it's very possible that the first relic detective will be massive, since this is the first kind of relic we should be able to see. In fact, we expect to see a huge improvement in current and upcoming surveys such as DESI and CMB stage 4, in some cases covering the full parameter space. And more generally, I want to leave you with this message that this decade is bringing a wealth of new and complementary data sets, and we will continue to exploit their complementarity and look for new ways to shed light on the dark sector. So stay tuned. Thank you.
Oh, thank you, Cora. We have time for a few questions. Thunder.
Yeah, thank you for that talk, Cora. I'm wondering, so with the models you showed for dark matter, like I guess there you're assuming that lambda CDM is the default, and you're like changing the model of dark matter itself.
That's right.
Could you also explore, I guess, like things like modified gravity theories with these like strong lensing systems, or I'm sort of like thinking like the degeneracy between dark matter models and modified gravity theory models, like how you might explore that.
It should be possible, since we are testing gravity. It may depend exactly on the specific model that you have in mind, but it's definitely, yes, it should definitely be a good way of testing modified gravity scenarios. I mean, there are many of these scenarios that I don't know if you wanted to know more generally or specifically if you have something in mind, but definitely it's a good probe.
Thank you. Yeah, I was just thinking about it more generally. Like, have you thought about like exploring that side of it?
I haven't been thinking about that, but I'm happy to talk with you, as I know you're curious about it. Yes.
Ramesh.
So Cora, I missed one important point in your talk. So you said that you try to distinguish between substructure or subhalos in the lens and other random galaxies in the line of sight.
Yes.
And you decided that it is not substructure, that it's probably line of sight galaxies. How can you tell the difference from lensing?
Yes. So great question. So they have Okay, so they have different effect in the convergence, but at the level of the curl, the line of sight halos produce a curl, while the subhalos do not produce a curl. So different lenses at different redshifts will produce a curl on the deflection field, while subhalos will just produce the convergence field.
Oh, that is wonderful.
Yeah.
Because the subhalos are all at the same distance.
At the same plane,
So
exactly.
just one potential, effective potential.
Yes.
I didn't realize that the different distance can.
Yeah,
introduce a curl.
yes, I should have
That's
mentioned,
what
but
the
we-
picture, I guess, shows.
I didn't talk about the curl, but we pointed this out in the paper in our first paper of line of sight halos. Yeah.
Very interesting. Thank you.
Yeah, cosmologists have gotten a lot of mileage out of separating curl-free divergence.
Curl, yeah.
Yes. We're used to it.
I was curious whether you were optimistic or thought about what you thought about non-gravitational ways to study subhalos. So they might not have stars themselves. They could knock into things that do have stars. And I know some people work on this kind of things. So wondering if you were optimistic if that's a good way to search for these things.
Sorry, for looking at the stars?
Yes, looking at, for example, subhalos knocking into things that have stars, like streams or something. Do you think that's an optimistic way to search for something?
So you're talking about non-gravitational ways of looking at subhalos by looking at the bigger mass subhalos with stars in them, or
Well,
looking
for
at
example-
gravitational waves?
So, for example, one technique you see is, you have a stream of stars across the sky. And there's a
Streaming.
break in it, then that could be a subhalo knocking into it.
Absolutely, yes. I have not been doing work with this, but I know, for example, Ana Bonaca has been doing a lot of work on this. Yes. That I mean, I am not an expert on it, and I have not been doing work on it, but it's definitely, I think it's a promising avenue to pursue.
And you can only do that in the Milky Way, you think, not in other galaxies.
The stellar streaming?
Maybe not for stellar streams, but just, I was curious if you're in your observations, you think it's only gravity that will be the signal that you can expect, not something in light.
So for what I'm doing, it's just gravity, but I don't know. But I mean, with you could apply other ways, but yes.
Thank you.
And so, yeah, I think you were first.
Okay. So for these asymptotic slopes, you said they're very small scales.
Yes.
Are you sensitive to baryonic physics and
Great.
our uncertainties in galaxy evolution?
Yeah, I was waiting for that question. I always get that question. Who is going to ask me about the baryons? Because I didn't talk about them. So first of all, I should say, we are having the same, we are eager to look at simulations. The simulations that we looked at don't have baryons. We're eager to get simulations with baryons, and we are I am very welcoming to anybody who has this type of zooming simulations with baryons. Now, to go to your question, the power spectrum. So here, this picture over here, yeah. So the power spectrum, so baryonic structures, say like giant molecular clouds or globular clusters, should start kicking in at scales that are smaller than about 10 inverse kiloparsecs. So that's why, that being said, that's why that I'm optimistic that at these larger scales, I'm using the redshift information, those will not kick in. But that being said, I think this should be done with baryons in the simulations. The only reason we didn't do this with baryons is that we don't have a handle on those simulations. But
Thanks.
And also, we have an audience on Zoom, and you're welcome to type questions into the chat. So Rohan will read them. So we're good. Okay. And yeah, Jesse.
Yeah, so you said there's around 3, if I read the number
Yeah.
correctly, 3 proposed subhalos.
with gravitational imaging, with
Right.
that technique, yes.
So are they all debunked, or should we be like excited?
No, they are
That's
not
big news.
debunked, right? So they are substructure and they have been detected. It's just that we think they're not subhalos, but we shouldn't use the word that word, but like they have been detected. There is something there. It's just that we don't think there's a pillar. No, we haven't looked at all of them.
Gotcha, because there are like recent papers that all claim like first detection of dark matter subhalo. So I was wondering if we're late on the news. Like,
They are a first detection of dark matter clumps, I would say, yes.
oh, cool.
But I don't know all of them. I mean, I only showed you the results for this one, and we have preliminary results for others that I'm not quite ready to show yet.
And are these statistics significant enough for you to derive like an abundance of subhalos, or is it just too few to?
Right. So that's the thing about direct detection, is that you get, we will be able, hopefully, to detect more than a few. But for now, there are some studies that put constraints on warm dark matter and different dark matter scenarios with a few detections. But of course, I think that the promising route for that is looking at the statistical detection, where you expect to see a huge number of low mass subhalos, and that will be more telling. But there are constraints on different dark matter scenarios using just a few, and there will be better constraints in the future.
Thank you.
We welcome questions from upstairs also.
I think Charlie had a question.
Oh, yeah.
I think that.
Arjun has a question.
So 10 to the 9 as the mass is interesting. I was wondering whether you think that that's the limit to which we cut off substructure at, or should we really be concerned about subhalos that are much lower mass than that? And the reason I ask is partly because of all of the subhalos we find in these lensing systems are could be line of sight halos. There must be some degeneracy between the mass of that subhalo distance that implies that.
So yes, there is a degeneracy. 10 to the 9, about 10 to, so the sensitivity, the sensitivity has been claimed to be 10 to the 8, but there it was it depends also on the halo mass function. It's a whole different story. In fact, we are thinking, anyway, I will answer to your question, but yes, I think with the current level of noise, with a few orbits of HST, we are not going to go below 10 to, I don't think that's possible to go below a few times 10 to the 8 at most. It depends on the halo, on the subhalo mass function that you're using. And in fact, we are doing work talking about this. We are trying to breach the definition of halo mass function to look for other observables that are not necessarily linked to the mass, like the inner density profile. But that's another story.
Okay.
I don't know if that answered. Yeah.
Okay, last question.
Here's a quick question. I don't know if you could give a number just for what we can expect for the upper limit of the SUSY breaking scale. You mentioned 70 TeV you got with the.
For these kind of gauge-mediated models, yes.
Yeah. So what's the kind of landscape there in the next 5-10 years?
It depends on, so that's kind of like if, tens of TeV is the landscape for future collider experiments.
Yeah.
So it's kind of, closing the gap between the two.
Okay, well, thanks for the excellent talk and the discussion. Nobody's allowed to leave until we're done with the food, though. So let's thank Cora again.
Okay, great, agreed, thanks. Okay, cool.